Okay. So what we have started discussing last time is quantum statistics. So in order to describe statistical mechanics in the quantum case, we know that a microstate corresponds to wave function of the whole system, and then if we want to compute, if we want to consider an ensemble will be a collection of microstates. Okay, but this k goes from 1 to is curly n. Okay, so and then we have to construct ensembles where we consider all the microstates which are consistent, which correspond to a particular macrostate. Okay. So of course these wave functions are all wave functions of identical copies of the system I'm considering, so they will have an evolution which is given by Schrödinger equation with the same Hamiltonian. Okay. And so what we have seen is that the central quantity we need to consider is the density matrix. The density matrix is an operator which can be written in general in terms of the ensemble in this form, in the bracket notation. Okay. So or if you want, if you expand these eigenfunctions in a complete orthonormal basis of eigenstate of the whole system, then this can be written as so each of these copy of the system will have its own expansion with coefficient I and k, and so the matrix element of the density matrix between states n and m, which is just, if you want, I can write it like this. Will just be 1 over n sum over all the members of the ensemble, a n star of t, a m of t. Okay. And so this makes it clear that, for example, if I look at the diagonal elements of this of the density matrix, I will have an average over all the members of the ensemble of an modulo square, which is just the probability that in a copy k of the ensemble I will find my system in state n, and so this is this will be the probability that in the ensemble one member of the ensemble taken at random will be in state n. Okay. And okay, so So in terms of this, if we have a, how do we measure expectation values of, how do we compute expectation values of physical quantities? Physical quantities in quantum mechanics are operators. So if we want to compute the expected value of a certain function g, what we will have to do is to take the expected value of this operator in any of the members of the ensemble, and then average over all the members of the ensemble. Okay. Now, in particular, if you now introduce an identity operator here, an identity operator here, so the identity is just sum over n times n. So if you insert it here and here, then you can see that this will be 1 over n, sum over k. So this will give me a n star. So sorry, and then you have a sum over n for this and a sum over m for this. So this n times ck will give me a star n k. So this also depends on k, sorry, for the system k. And then I will have the matrix element n m of g, and then a m k, right? And now you see that if I take 1 over n sum over k of this is just the density matrix. Okay, so this is just the sum over n and m of rho n m times g n m g n m. I have a problem with the indices, so let me see. Let me get this right. Okay. Okay, so yeah, I'm sorry. I mean, this is am star. Okay. So an is n, ank is an ck, right? And a star kn is psi n, is the opposite, right? Okay, so this is rho n m is ank mk star. Okay, and so here I have that this is actually rho mn. Okay. And so you see, this is, I can write this as the trace of rho times G. Okay? So this implies that the measure which you know that the trace is an invariant. It's an invariant under the choice of a basis vector. It's invariant under orthonormal transformation. So the measure, physical measure of observable will be independent of which basis I choose. Okay, this is very important. Okay, and okay, so this is, and also it makes it clear that once we know this density matrix, we can compute all the observables in our system. Okay. So the density matrix is the important quantity. Okay. Now, if we consider a system in thermal in equilibrium, so which is not subject to external forces, then we can ask ourselves what is the evolution of the density matrix, and this leads us to the Liouville to the analogous of the Liouville theorem, because if you take a h bar times rho n m, the time derivative of this, then see there are two ways where I can take the derivative. One is here and one is here. So I have a h bar divided by n sum over k a k dot n times a star a k star m plus a k n a k star dot m, right? And of course I know that the I h bar a n dot is equal to the sum over m h m n times a m for from this is the Schrödinger equation for the whole system, and these are the matrix element. It just derives from the Schrödinger equation, right? So if you take if you take this the bracket notation, you take direct product with eigenfunction n here, and you take an identity here, then you will just get this, right? so if I use this equation here, what do I get? I get that, so here 1 over n factorial I h bar times this is going to give me the sum over an m prime of h n n prime times a m prime a star m, and this is a index k. And on the other hand, if I take the complex conjugate of this, I will have that there is a minus sign, and there is there is h star m prime, which is just h m prime m times a k m, and a star k m prime. Sorry, this is n. Okay. And if you look at, so this is, and there is a sum over k, of course. So this 1 over n times this and this gives you the density matrix again. And what you find is that this is the sum over n prime of h n m primes times rho m prime m minus h minus rho n m prime h m prime m. So this is just a commutator between h and rho, and so this is just so what we find is that I h bar times the derivative of the operator of the density matrix is equal to h, the commutator of h with rho. Okay. And this is a very important result, and it's the analog of Liouville theorem, because it tells us that rho, the density matrix, is a function, must be a function of the Hamiltonian. Okay. And then I mean, depending on the physical system, one can derive different form of the density matrix precisely in the same manner as we did for classical systems. Okay. Also, the other important thing is that, of course, in the energy representation, rho will be diagonal. Okay. And now we can discuss the different ensembles in the quantum case. Yeah? Okay, so in the Liouville theorem, if if you remember what we did with the Liouville theorem, essentially we said that we had, this is a classical case, so we have a density which depends on the position, on the positions and the momenta of all the particles, right? And then I wanted to compute the rho dot of this. And what we found is precisely that this is what we find actually is exactly an expression which in classical mechanics one usually writes like this, where these are called the Poisson brackets, and this is exactly the analog of that. And so the statement that rho is a function of h is exactly the statement that this is equal to 0. And the function that, so if the statement that you are considering a stationary state, so an equilibrium state, is the statement that rho must be a function of h. So if you set this equal to 0, it means that rho must commute with h. So rho is a function of h. Okay? So these two statements are exactly the same statement. Okay? And so okay. Okay, so now we can discuss the different things ensembles, and so in particular, so the microcanonical ensemble. In the microcanonical ensemble, we study an isolated system with a given number of particles in a given volume V and with a given energy E. Actually, since the energy levels are discrete, it's better to consider systems where the energy levels of the system are in a range, in a small range of energies. Okay, where this delta is much smaller than E, and eventually delta is infinitesimal. Okay, so that all so the density then you can discuss the in the energy representation. So the density operator is a diagonal operator. So it will be equal to some rho n. So it will be proportional to a constant times delta n m, and this constant in general depends on n. And now this constant here is the probability to find the system in a given energy in a given energy eigenstate, right? And so what we have to say, I mean, in the microcanonical ensemble, this constant can be either a given number, let's call it 1 over gamma, if the energy eigenstate of, if the energy level is in this range, otherwise it's 0. Okay? So this is the microcanonical ensemble in the quantum case. Okay, and then once you have so this number gamma must be such that the sum over all the states of the probability to find the system in state n, this must be equal to 1, right? And this condition gives you this normalization factor gamma. And this tells you that gamma must be the number of energy eigenstate with an energy in this range. Okay? So it is precisely the number of microstates which are consistent with this macro state here. Okay? And then from this you get that you can compute the entropy as being k times the logarithm of this number gamma. Okay, and from this you can, if you compute this number gamma, then you know the entropy, and you can compute all the thermodynamic properties of your system. Okay. So in particular, if there is only one eigenstate of the energy which is in this range, then your gamma will be equal to 1. This is typically what happens when the temperature goes to 0. Your system goes to the ground state. So there is only one state which is possible for the system. This means, in particular, that so this means that, of course, the entropy will be 0. This is the third law of thermodynamics, Nernst's theorem. And from the point of view of quantum mechanics, this means that this state will be represented by a pure state. Pure state means that all the states of your ensemble will effectively be the same. Okay, so they will all be equal to the same energy eigenfunction for all members of the ensemble. And or if you want that your matrix element, your density matrix, in general will be equal to a single term, can be expressed in terms of a single term. So in this case, for a pure state, so the density matrix satisfies this property that rho squared is equal to rho. Essentially, the density matrix is a projection on the is a projection operator on the ground state. In the case where you have just one pure state, so the density matrix becomes a projection operator on the pure state, and this just tells you that if you project twice then it's equal to projecting once, and if you project more than once, it's equal to, has the same effect of projecting just once. And in order to see this, we can compute the matrix element nm of this. And this is just equal to the sum over L of A n A star L times A L A star M, where I've used this expression for the density matrix. And of course now you see that this is just the modulus square of the wave function. The sum over L of this is equal to 1. So that this is exactly equal to A n A star M, which is equal to rho n M. So if this is true for all the, if all the matrix element of the square of rho are equal to the matrix element of rho, so it means that rho square is equal to rho. Okay. So if so, this corresponds to a pure state. Now, if gamma is larger than 1, if gamma is larger than 1, then the entropy will be positive, and this will correspond to a mixed state. It's called generally a mixed state. Now, so as we've seen in the microcanonical ensemble, you have this property that the density matrix in the energy representation is diagonal, and all the diagonal elements are equal. Okay, because essentially this comes from the fact that we assign equal probability to all microstates. Okay, so all the microstates which are consistent with the constraint of having essentially the same energy are given the same probability. Okay, again the same statistical weight. Now, if we take a different representation, then in general we could have a density matrix which is not diagonal, but still the matrix element on the diagonal would represent the probabilities to find the system in the different states. Okay? And we should expect that these probabilities are the same, because all these states are consistent with the macroscopic state. Okay? So in general, we would expect that the diagonal elements of the matrix are also equal to one another, and are equal to 1 over the number of states, of microstates. Okay, are equal to 1 over gamma. Okay. Now, it is also true that in the off-diagonal elements of the density matrix, in any other representation, will also be 0. And this is essentially because when we construct the microcanonical ensemble, we take we take our density matrix as an incoherent superposition of states. Okay, so these states are this is a mixed state of all the wave functions which are consistent with a given energy. Okay, and so, for example, the matrix element M which is given by this. So I can write this matrix element separating in this coefficient the absolute value and the phase. Okay, so I can write A n k as say the absolute value of the modulus of A n k times a phase. And then the fact that rho n n is equal to does not depend on n suggests that this coefficient do not depend on n. Okay, so that you can essentially think that in your superposition, the amplitudes are all essentially the same. And what really changes between one eigenstate and the other, I mean, this is a rough argument, but what really changes between one member of the ensemble and the other is the phase. Okay, and so that when you compute this is essentially approximated by an average of this A squared times a difference between phases between the different eigenstates. So, and so generally, if n and m are different, then in different members of the ensemble, the phases assigned to these states will be completely different and unrelated one to the other. And the effect of this is that when you take the average over all the states, this will give you 0. Okay, so the fact that the diagonal, so the matrix, the density matrix is 0 is a consequence of the fact that you have an incoherent superposition of different states whose phases are random one with respect to the other. Okay, so so this means that you expect that now, of course, you see this is consistent with the fact that rho is a projector, of course. But this is indeed a consequence of the fact that we want to consider an ensemble of systems which are equiprobable, essentially. Okay, and this means that the only, let's say, structure of the density matrix in the canonical ensemble is essentially a diagonal one. Okay. Okay, so this is the canonical ensemble. How do you if we want to describe a system which is in thermal equilibrium with another system, then you need, at a certain temperature T, then you need to introduce the canonical ensemble. And we know what we have to do in the canonical ensemble in the energy representation. In the energy representation, we know that a state with energy En should have a probability which is proportional to e to the minus beta times En. This is precisely because of the same consideration that we have done for the classical system. And this means that in the energy representation, the density matrix is given by e to the minus beta times En times delta n m. En are, of course, the eigenstates of the system, divided by the partition function. And the partition function Qn is just the sum over all the states of e to the minus beta En. Okay, over all the possible state of the system. So this is in the energy representation. In a generic representation, well, you can write so this means that as an operator you can write the density matrix is a sum over energy eigenstate of so of course if I write in the energy representation, I can write the density matrix in this form, right? Which is which clearly will have these matrix elements, right? Now this means that I can now I can write this as e. I can take e to the minus beta times the Hamiltonian. I can substitute for e to the minus beta times the Hamiltonian here, and sorry, actually, and I can write it here. And I can divide by Qn. This is clearly equal to the identity. So this means that the density matrix in the canonical ensemble is just given by e to the minus beta times the Hamiltonian divided by the partition function. And of course, this is now true in any representation, because I have expressed the density matrix in terms of operators. So then I can take now, I mean, this is an expression which is valid for any representation. And so, and again, here, if you want to compute any expected value, so in general, the partition function Qn can be written as the trace of e to the minus beta times h. Okay. So in any representation, so this is so this is true in the energy representation, but in any representation, this would be true. Okay, because the trace is invariant under any orthonormal transformation. So from this you can write the expected value of any operator as the trace of the operator times e to the minus beta h divided by the trace of e to the minus beta times h. So these are the formulas which essentially the problem, the whole problem in the canonical ensemble again is to compute the partition function, to compute this object, because once you have this object, as in the classical case, you can take the log multiplied by kt, and that is minus the Helmholtz free energy. Okay, and you can derive everything. Now, what about the grand canonical ensemble? So, in the grand canonical ensemble, I'm considering systems which are in thermal and chemical equilibrium with a larger system. So, the number of particles can change, fluctuate. So this means that when I construct my ensemble, my wave functions must belong to Hilbert spaces with a different number of particles, right? In my psi k, this psi k will belong to Hilbert spaces with different number of particles. Okay, and still, any of these, in any of these, for any of these members of the ensemble, the eigenfunction must be an eigenstate of the number of particles. Why? Because the dynamics conserves the number of particles. Okay. And so the Hamiltonian dynamics of the system, so if I take a system with n particles and I follow its dynamics, then the number of particles will be conserved. Okay? Then I want to consider a superposition of different states with different number of particles, a distribution of systems with different number of particles. But in each of the copies of the system in my ensemble, the number of particles will be conserved. So this eigenfunction should also be write it like this. Should also be eigenstates of the number of particles. Okay. Then if this is true, then you can show that even rho must be a function of the number of particles. Because I mean, if you can compute this this commutator very simply as 1 over n sum over k psi k n. And now you see that if n is an eigenstate of, if psi k is an eigenstate of n, then this will be identically equal to 0 for all terms k, right? And so I have to find density matrix which are a simultaneous function of n and h. Okay, and I can do exactly the same derivation as we have done for the grand canonical ensemble, and the result is that if I am in a representation which is diagonal in n and h, so the probability to be in a state with a given energy En and a given number of particles n will be proportional, will be essentially proportional to a constant times e to the beta times mu times n minus beta times En, which means that precisely as in the canonical ensemble, I can write the density matrix, and this constant here is just a normalization constant because I have to because I want that if I sum over all the possible states, this will also be dependent on the state. Then the density matrix should sum up to 1. No? I mean, the trace of the density matrix should be equal to 1. So this constant C, 1 over C should be equal to the sum over n of e to the beta mu times number of particles minus beta times En. And I can do this this sum by first considering all the states with a given number of particles n, and then sum overall number of particles n. And here, so I will have e to the minus e to the beta mu times number of particles. And the sum which I have here is just the canonical partition function for the number of particles n. So this is precisely the grand canonical partition function which we have discussed in the canonical, in the classical case. And so what I have to do is to compute this grand canonical partition function, and then I can compute the density matrix. Exactly as in the case before, in other, so I can write then the density matrix. Yeah. Because this is the probability to find my system in state n, okay? And if I sum over all the n, then this must be 1. So the sum n over all the possible values of n, well, this should be 1, because this is the probability that the system is in state n. It must be in some state. Okay? So if I sum over all the states, the probability should be 1. Very good. So in general, in the grand canonical ensemble, I can write the density matrix as E to the beta mu times the number of operators, the operator number of particles times beta h divided by the grand canonical partition function, which is and the grand canonical partition function in general can be written as the trace of e to the beta mu times n minus beta h. Okay? So this is the analog in general of the grand canonical ensemble for quantum systems. And again, if you want to compute expectation values, you have to take the trace of the operator times rho. Okay, so now let me try to discuss more in detail what are the differences between which we encounter in quantum statistics with respect to classical statistics. And so one of the main issues is that particles in quantum mechanics are indistinguishable. So if you have different particles which are identical, which have the same physical properties, then you cannot distinguish these particles. And the reason why can't you distinguish two identical particles? By which principle? Sorry? How would you distinguish two particles? So in classical mechanics, how do you distinguish two particles? I mean, position? Yeah, for example, position. Okay. So can you measure the position of a particle in quantum mechanics? Huh? Yeah. Yes. So because of the uncertainty principle, you cannot really measure the position of a particle with infinite accuracy. Okay. So this means that you are not able to follow all the particles. I mean, even if you imagine you knew the position of the particle at a certain time, you could not follow their dynamics over time. Okay, so it is really impossible to distinguish identical particles. Okay, so this has very profound consequences. So let us discuss systems of identical particles. So if you have systems of identical particles, it means that your Hamiltonian, which can be expressed in terms of position and coordinate operators, is actually a sum of identical terms. Well, say I should probably use a small h here. So where this function or this operator is the same for all, has the same functional form for all particles. Okay. Okay, so from a quantum mechanical point of view, you want to look at the eigenstates with a given energy of this system. And how can you construct these eigenstates? Well, if you have a solution of let's say these are operators, if you have a solution of the single particle Hamiltonian, where this is so this Q is clearly the collection of all positions. This is just one position. So this is a function of, say, particle 1. Okay. So imagine that you have a solution to this equation here, and this tells you that you have some discrete energy levels, because we are going to look at a confined system, so energy level will be discrete. Then the way in which you can construct the eigenstates is by combining single particle eigenfunctions. Okay, and so this operation is so you will have that. So this operation, if you want to construct this function from these functions, essentially you have to figure out how many particles will be in a given eigenstate, single particle eigenstate. Okay, so you have a problem of putting particles into eigenstates. So the key object will be the occupation number. So NL, which is the number of particles in eigenstate L. Okay, a single particle eigenstate L. Now, so this number here, if you want to construct an eigenstate with a given energy E, well, this number of this occupation number has to satisfy two properties. First, that the total number of particles is equal to n. And the second thing is that if you want an eigenstate with a certain energy E, then this must be true. Okay? And then one idea of how you could build a trial wave function with those number of particles and that energy is by putting, say, for example, the first n1 particles in energy level 1, the second n2 particles in energy level 2, etc., etc. So, for example, have the product from m equal to 1 to n1 of u epsilon 1 of qm times the product of m equal to n1 plus 1 to n1 plus n2 of u epsilon 2 of qm, etc., etc. Okay, so this is in this way you construct a wave function where the first n1 particles are in state 1, the second n2 particles are in state 2, etc., etc., until now this state is what you would do if you were a classical minded physicist. But the problem of this with this function is that it is a function where you really can distinguish between particles. Okay, so how do we formalize this notion that particles should be indistinguishable? So one way to formalize it is to by the permutation operator. Okay. The permutation operator is something you can define. So if you have a function of n arguments, then you can define the permutation operator as that argument, that operator which permutes the arguments of the function. Okay. Where these P1, P2 up to Pn are a permutation of the integers 1 to up to n. Okay? So P is the permutation P which I'm considering is precisely this permutation. Okay? So you have n factorial permutation operator of this type. Right? Now, so one way to say that particles are indistinguishable is to say that the eigenstate must be, so the wave function must be an eigenstate of all permutation operators. Because if it is so, then you cannot really distinguish. Okay. So notice, so what are the eigenstates of a permutation operator? So the permutation operator has this property that if you take twice a permutation, then you get the identity. Okay? So if you swap for a simple permutation where you just interchange two elements, if you interchange them twice, then that's and every permutation can be decomposed in pairwise changes. Okay. Indeed, you can define the sign of a permutation as the number of pairwise changes that you have to do to go from the natural sequence 1 to n to P1, Pn. Okay? So, for example, if you have 1, 2, 4, 3, this is a permutation of the first 4 numbers, which is a sign equal to -1. Because you just need to change one pair, okay? Instead, a permutation which is say 2, 1, 4, 3. You need to interchange both these two and these two. So the sign of the permutation is 1, because you have to do two swaps, okay? So in general, so this means that the eigenvalues of this object can be either 1 or minus 1, okay? And in general, it will depend on the permutation. So the so the eigenvalues of the permutation operator are either will be essentially minus 1 to the sign. It will be essentially the sign of the permutation. Okay. Now, how do you do? So now imagine that we want to do a symmetric an eigenstate of all permutation operators. So how do we do this? Well, there are two ways. One, if we do a symmetric combination, so we can construct a symmetric wave function by just taking 1 over the square root n times the sum over all permutations times p of, for example, this of this function here. Okay, so this means that I am taking I am considering all the permutation with the same sign, and this 1 over n factorial is clearly because I want if this is a normalized wave function, I want also this to be a normalized wave function. So there will be n factorial terms when I compute the modulus square of this. Okay, so this is one possibility. So the other possibility is to consider antisymmetric wave functions. So this is psi a of q1 qn is again 1 over the square root n factorial because of normalization. I take the sum of all the permutations, and then it's just minus 1 to the p times now this will be an eigenfunction which is symmetric, so p times Cs is equal to Cs, and this will be an eigenfunction such that if I operate with a given permutation on this, I will get minus 1 to the p times Ca. Okay, so these are both eigenstates of permutation operators. Okay, and so this corresponds to two different choices which we can take of for the wave function of a system of n identical particles. So this corresponds to two different types of particles. And it so happens that nature have chosen to have particles of both types. Okay, so these are called bosons, and these are called fermions. And bosons will obey a statistics which is called Bose statistics, or Bose-Einstein statistics. And fermions will obey statistics which is called Fermi or Fermi-Dirac statistics. And it all, in the end, will boil down to how we will count the states, okay? As we are going to see in a moment. So to recap, so the so indistinguishability means that I have to change. I cannot consider wave function of this type. I have to either consider symmetrized or anti-symmetrized wave functions. And these will correspond to different types of particles, okay? Now this also corresponds to, you see, while there are essentially how many functions of this type can I build? If I'm given a certain set of occupation numbers, so then there are a number of particles or functions of this type which I can build, which is equal to essentially n factorial divided by product over I of ni factorial, right? Because of course, I mean, n factorial permutation I can do of the arguments, but any arguments which I do, any permutation which I do inside any of the group will not change the function, right? Okay? So there are these many different states where I consider the particles as distinguishable, okay, even though they are identical. How many functions of this type there are for a given set of occupation numbers? I give you the occupation numbers, and I tell you compute the symmetrized wave function with those occupation numbers. How many possible functions of this type you can come up with? How many? N factorial. Huh? One. One, because I'm taking all the permutations already into account, and I have to find something which is symmetric with respect to all permutations. So there's only one function of this type I can build. One function of this type I can build. Okay? So this tells us that the number of states, microstates, which correspond to a given set of occupation numbers, for this case is equal to 1. And the number of states, microstates, which correspond to a given occupation number is equal to 1. Okay? So this is the key difference between quantum statistics and classical statistics. Okay? And it comes from the fact that particles are not indistinguishable. So it comes from Heisenberg uncertainty principle. Okay? So you may remember that the fact that particles, we were considering distinguishable particles was a problem in classical statistical mechanics, because we were saying we were getting an entropy which was not extensive. So we had the Gibbs paradox. So the Gibbs paradox just corresponds to modifying the number of ways in which we count the particles by divided by 1 over n factorial. Okay, so modifying the way we count by just dividing this by n factorial, so going to from this to 1 divided the product of I and I factorial. Okay, so this is still different than this and this. So the Gibbs factor 1 over n factorial is not really enough to really take into account particles are really indistinguishable. Okay, so this fact will have consequences which are physical and that one can measure. Okay, so let me take just the last 5 minutes to really derive these consequences. And so in this case, so it is easy. I mean, if you construct if you construct function in this way, then taking the linear combination, the average over all permutation is an easy thing. So there is a particular way to construct completely antisymmetric wave functions, which is called from single particle eigenstate, which is called the Slater determinant. Do you know this? Have you seen this? Okay, very good. So, and of course, Slater determinant encodes the fact that, in a very simple way, the fact that if you take this function, you cannot have more than one particle in the same energy state, because you will have two columns which are the same, and then the determinant is 0. And you cannot have two particles which are in the same position, because otherwise two rows will be equal, and the determinant will be 0. Okay? So this encodes essentially the Pauli exclusion principle. Okay? And which is very important. So let me consider a really simple case of two particles which are identical and do not interact, and they are confined in a box which I'm considering, for simplicity, for the moment, to be of volume 1. Okay, so I'm not considering the one. So what I want to compute is what is the probability to find a particle in position R1, the other particle in position R2. So what I want to do is to compute this matrix element of the density matrix. And I'm considering two particles in equilibrium at temperature T, which is equal 1 over K beta. Okay, now, okay, so how do you do this calculation? So this calculation is, so the wave function which you have to consider, so this R1, R2 are effectively plane waves, right? So the eigenstates, so these are free particles, so the Hamiltonian is just p squared over 2m plus p2 squared over 2m. So it's just the kinetic energy of the two particles, and and the wave function is plane waves, eigenfunction of the momentum, and but I have to consider either symmetric or antisymmetric wave function. So I will have two momenta, k1 and k2, and I have to symmetrize. So this will be 1 over square root 2, and then I have e to the I k1 r1 plus I k2 r2 plus or minus, plus for bosons and minus for fermions, e to the I K1 R2 plus I K2 R1, right? So this is the wave function. And then what I have to do in order to compute this is to take an integral. There will be a constant, normalization constant. And then I have to take an integral on dk1, dk2 of the energy will be just e to the minus beta, e to the minus beta, the energy. So h k squared over 2m, k is times k1 squared plus k2 squared. Okay, so this is e to the minus beta times the energy. And then I have these two things, right? So let me call this, say, this, say, yes, this is 1, 1, 1, 2, and this is 2, 1, right? Okay, so now you have to consider these times the complex conjugate to this, and then you will have 4 terms when you do the expansion. So the first term is this times the complex conjugate of this, which is 1. Okay. Then you will have this times the complex conjugate of this. There is a plus minus term here. And you have e to the I k1 r1 minus r2 plus I k2 r2 minus r1. Okay? Then you have this times the complex conjugate of this, which is exactly the complex conjugate of this. If you do the calculation, I mean, it's trivial. With, again, with a plus minus sign. And then you have this times the complex conjugate of this, which is just 1. Okay. Okay, so now what you have is just a Gaussian integral. So this is, there is the square root of 2, which, well, but I will not, there is 1/2 here if you want. So the, so what you have here is, well, you have just, you will have just a Gaussian integral, which just gives you a constant, which does not depend on, the positions. Okay, so I want to find how this thing depends on the positions. Okay, so I'm not interested in particular in this constant. And which multiplies 1 plus or minus. Well, these two integrals will give you essentially the same result. And then you can do this calculation very easily, and you will get e to the minus 2 pi 1 minus r2 squared divided by lambda squared. Okay. Where this lambda is what is called the thermal the thermal wave function, the thermal wavelength. And it's you can just read it from here is, but since there is a factor, so it's h bar times 2 pi beta over m to 1/2. So now you see this plus correspond to bosons and this minus correspond to fermions. So you see first that so what do you expect in the classical limit? In the classical limit, in classical in classical mechanics, you expect that this object should just be a constant. It should be just 1 over the volume, because or 1 over the volume squared, because any particle can be in any position, so does not really depend on the coordinates of the two particles. Whereas this depends on the relative coordinates, and this dependence is particularly important when the distance becomes less than lambda, than this thermal wavelength. And so, and how is this dependence? What type of dependence do you have here? So you can see that if you plot this function as a function of R1 minus R2, so this matrix element here, so for the case of the bosons, so imagine that this is the classical limit. If this were the classical limit of classical mechanics, so in the case of bosons, this function will be higher. It will go at twice the value which you get in classical mechanics. So this would be the value which you get in classical mechanics. You get twice the value. Whereas in the Fermi case, when you have the minus sign, when R1 goes to R2, you will get to 0.
So we are saying R1 minus R2 can be 0. I mean, all particles can be...
Yes, in this, in the case I'm discussing, these are really point particles. So R1 minus R2 can be, I'm not considering particles with a finite radius, okay? So they can really, well, they can be 0. So, but you see the effect of the distinguishability of particles becomes particularly relevant when the distance between the particles is less than lambda. Yes?
Because we said we write the Hamiltonian like kinetic energy term, right, for each particle. And then now we are saying R1 minus R2 can be 0. And does it make sense?
I'm considering a matrix element of an operator. This I can compute. And you will tell me the probability that I will find these two particles in R1 and in R2, right? So it's just a probability, no? And so this probability will be enhanced in the case of bosons, and it will be suppressed in the case of fermions, right? And so the last thing, because we are quite late, so is when do we expect to see physically this effect to be important? Well, this so the you can think that the distance between the particles. So typically, the distance R1 minus R2 between the two particles will be of the order of the volume divided by the volume per particle. to the 1/3, right? Okay, so when this thing is much less than the volume per particles to the 1/3, you will have I mean, essentially you can neglect quantum effects. Okay, and so this corresponds to the condition that say yes, h bar times 2 pi over m kt must be much less than v over n to the 1/3. So it means that either you consider a system at very low density, so that this is very large, or you consider systems at very high temperature. So at high temperature and low density, you can neglect quantum effects. But if you are at low temperature, or if the density is high, then quantum effects will become important. And we will see that there are some effects of quantum statistics which become important even at room temperature, because the density will be very, very high. Okay, and this is particularly because of Pauli exclusion principle, which makes so that there are even quantum systems at room temperature where the density is so high that this condition is not satisfied. Okay? So see you on Monday.